Hi, everyone. This is a recorded meeting for the Unit 4 final exam for ESSC 101. I'm mainly going to go over the review questions. I also wanted to go over a little bit about information that you can use to study for the exam. So, okay, being the final, there is this expectation that it's going to be cumulative, but it is not. It is only based on Unit 4. So as far as the number of lectures and the amount of information it's covering, it's a little bit more like the first or second exam where there are not that many lectures. So it's lectures 20 through 25. So that's all of Unit 4. As far as textbook information goes, the textbook's pretty limited when it comes to information about geologic time and historical geology. That is typically covered in a separate class if you were going through a whole sequence in geology, and it's just kind of a subject that I sort of tack on to the end of a mainly physical geology heavy class. So I don't have a separate textbook at this time. I used to in the past. So the information from the textbook that you have, the physical geology book, is really just contained in chapter 8. So I think that makes it worthwhile to take the time, if you want to go through the textbook, take the time and go through most of the information in chapter 8. It's all relevant to the information for the final. The quizzes are always good to go back and study from. The lecture outlines always make a good study guide. And then these review questions make a really good almost like a practice final to see how well you're really retaining the information. So one thing that you can do is go back and do these review questions before you go through and watch this video. See how well you can answer them on your own from your own lecture notes. And then when you go back through here, just kind of make sure that you're on the right path and that your answers are tallying up with mine. So that's about all I've got as far as the information I wanted to kind of convey about the exam itself. As far as its weight in the class, it isn't weighted any higher than any of the other exams. So it's just like any other unit exam that we've taken in the class. It's worth 100 out of a total of 500 class points. So 20% of your grade, like all of the exams have been. What I'm going to do now is share my screen so that you're going to be seeing a bit of an infinity loop for a second here. And then I'm going to go in to Moodle, go through all of this Unit 4 information. I'm scrolling down all the way down to the bottom. Under the Unit 4 review exam information, you have an old version of this review video that by the end of the day I'm going to replace with today's video, and then the review questions. So if you go ahead, open up these review questions, that's what I'm going to be filling out. I'm going to be reviewing for the exam today. I'm going to just make it a little bit bigger so that you guys can see this as well as I do, because I know you're viewing this on a number of different devices. So always important to put all this information into your own words. One of these questions is the study, extra credit assignment question, but whether you're doing it for that purpose or just for your own purposes, it's the putting it in your own words and translating it out of the way I think and into the way you think that's really crucial. So going through these, they're all, basically following the subjects of the individual lectures within Unit 4. The first 2 lectures are really critical, and they're more heavily covered in the book chapter. They're a little bit more about how we think about geologic time and what are the rules. How do we begin to process all of this information and mold it into some sort of a story that tells us about Earth history? So that's relative and absolute age dating. That's really actually the first 3 questions here are all based out of lectures 20 and 21. 22 is when I start going over geologic time, starting with the geologic time scale, and then going more towards the time scale itself, and then going more towards sort of a chronology of Earth history, starting from the beginning, going through all of the eons and eras, telling it in sequence, and going up to present. So when you're going through this information, I would suggest you concentrate more heavily on lectures 20, 21, and the first half of 22 when I'm covering the basics of geologic time, because that information is all going to be heavily featured on the exam. There's going to be a little less detail from the latter half of 22 through 25, because that's when I actually start going through Earth history. And I cover it in a lot more detail in the lectures than I do on the exam. And the reasoning for this is prior to recording these lectures, when I've written all of these versions of the test in the past, I used to not have quite as much time to cover geologic time and actually cover the whole timeline like I do now. So I always know now I have a fixed 25 lectures. In the past, I had, maybe 1 or 2 class periods to cover all that information from 22 through 25. So it was usually done in a lot less detail. So kind of keep that in mind. Concentrate more heavily on 20 through 22. Don't get too bogged down into the details, 20 through 20, the latter half of 22 through 25. So first question here is, what is relative age dating? And then what are the principles? How are they used? So relative age dating, so plenty of room here. Relative age dating is the process of putting things in sequence, putting these events of Earth history in sequence so we can start to be able to tell the story. Relative age dating actually predates our understanding of how old the Earth is and how long ago some of these events took place. So we were able to tell a little bit of the story of the formation of the Earth and the early history of the Earth before we had methods available to date the age of the Earth. And that's why these two are really kind of separate disciplines. Relative age dating is older. So relative age dating is effectively just putting the events of Earth history in sequence. And this part's important, without assigning numerical ages to the individual events. So it's just putting things in story. What happened in sequence? What happened first? What happened second? What happened third? And so on. So the principles of relative age dating are effectively can be thought of as the rules. These are the rules that we use to be able to tell the story of geologic time. The most important one is called the principle of superposition. So the principle of superposition tells us how to read geologic time through looking at these layers of rock. You read a book from beginning to end. You read the Earth from bottom to top, because these layers of sedimentary rock are laid down in sequence. A sequence of sedimentary, let's say, undisturbed I cannot spell today. Undisturbed. Sedimentary rocks. The oldest is on the bottom, and the youngest is on the top. So this is the most important rule because it gives us a basis to start from. We know that layers of rock are laid down one on top of the other. So we know the older events recorded in the older rocks are going to be found stratigraphically lower. The more recent events, the younger rocks, are going to be found up higher. So that's a great place to start from. Then we look at all of the rules that basically sort of allow this to be so. And so I tend to combine these original horizontality and lateral continuity. These are kind of tied up into the principle of superposition, basically saying sedimentary rocks cover something like more than 75% of the Earth's surface. They're going to be by far the most abundant rocks found at the surface and the ones that actually record Earth history. So these are going to be the types of rocks that are going to be the most important to us. Sedimentary rocks are typically deposited in flat, horizontal layers and continue out and basically are the same thickness horizontally until you get to the end of that basin. Let me think about this. Yeah. So effectively, we know so far that sedimentary rocks are deposited in flat, continuous layers. So they are originally horizontal and laterally continuous. And the oldest ones are found on the bottom, the youngest ones are found on the top. So for the most part, you can almost just kind of ignore this second rule. It's the one that makes the first rule true, effectively. Now we get to the juicy stuff. What happens when you disturb a sequence of rocks? So the principle of superposition relies on undisturbed sedimentary rocks. This gets into the principle of, not spelled today, of cross-cutting relationships, i.e. anything that cuts through a sequence of rock has to be younger than the rock that it's cut through. So this applies to things called igneous intrusions. So this is molten rock that intrudes into other layers of rock, like layers of sedimentary rock, and then cools and solidifies in place. And this applies to faults. I just got a beep. Let me just make sure nothing weird's going on and the recording is still continuing over here. Yes. Okay. So igneous intrusions and faults. So fault is just a break in the rock. Are always younger than the sedimentary rocks they cut through. So the principle of cross-cutting relationships, anything that cuts through a pre-existing sequence of rock has to be then younger. So if you have a layer of sedimentary rock, an igneous intrusion intrudes up through those rocks, and then all the rocks are faulted, the sequence of events goes 1, 2, 3 sedimentary rocks, the igneous rock, and then the fault. So it allows us to, again, tell the story of when did these events that cause the igneous intrusion and cause the fault take place. We can put them as happening more recently than the deposition of the layers of rock. And so again, it's all just allowing us to tell a story. The principle of inclusions, the next one. Sadly, inclusions and intrusions sound really similar, but they actually mean opposite things. An intrusion is a new rock that is being formed within some sequence of sedimentary rock. So it, by definition, has to be younger. A principle of inclusions are older sedimentary rocks that get reworked and deposited in younger sequences. So the inclusion is always older. So the inclusion doesn't necessarily have to be sedimentary rocks. I know I said inclusions are older. Sedimentary rocks, we'll just go ahead and say rocks, or more typically sedimentary rocks, are older and get reworked. So if you've got an inclusion of something older in a younger sequence of rock, that not only tells you about the age of the inclusion, it tells you about the age of that pre-existing rock that had gotten reworked. So this is particularly useful if you have rocks that have been overturned. Basically, if effectively they've been disturbed in some way, then you always know that you always know what is older and what is younger, which is, again, the point of all of these principles. One or two last ones here. Principle of faunal succession. Fossils contained within sedimentary rocks are going to show the evolution of life in sequence the way that those sequence of rocks show Earth history. So fossils contained within sedimentary rocks and be used to date a sequence of rock. And in this case, it is unique to sedimentary rocks. Because fossils may be unique to that time period. And finally, principle of landscape succession. Erosional features. So these can be canyons, valleys, are always younger than the rocks they erode. So the example I use in the lecture is the Grand Canyon. The Grand Canyon's relatively recent. It's something on the order of 5 million years old, but the rocks it's cutting through are hundreds of millions of years old. So the rocks had to be there for the canyon to then slice and work its way down through those existing rocks. Another example I don't think I really referenced too much in the lecture is cave formation. The caves are always more recent than the layers of rock that cave has eroded through. So caves form as acidic water travels through fractures in limestone, and then those fractures widen over time. And then so again, the rock had to be there first for the cave to form through it. So it's just another example, in effect, of landscape succession. I've got a dog coughing in the corner over here if you're wondering what all of these sound effects are. I think we all have little colds. Okay, so that's relative age dating and the principles of relative age dating. So in a really big picture kind of view, these principles are telling us how to put these events in sequence. What are the rules that allow us to put these events in sequence? There are probably a couple of things with principle in the name that I didn't include from the lecture, like uniformitarianism, that are a little bit more broad. They're really just, giving us some insight into Earth history more broadly. So I didn't want to include it in here. But these are basically the principles that directly affect relative age dating. So I thought I would include those. So that's number one. That's basically lecture 20. In a really sort of broad overview with a little bit of detail missing. We cover things like unconformities, principle of uniformitarianism, some other things that are part of that lecture too, and some really good images. So I never want to make it seem like these reviews will actually suffice to teach you like all of a unit's individual subjects just in like 1 hour. It's always definitely worth treating these as a review of the lecture videos. So thought I would throw that in there too. So number 2 on here, describe how the age of the Earth is calculated. They're in here scientifically because I've had a lot of non-scientific answers to this question, but we're grounded in science here scientifically, and explain how we can make this calculation based on our understanding of how the Earth was formed. First, any scientific calculation of the age of Earth or Earth materials comes from our understanding of radioactivity and radiometric decay. So first off, we date, well, we do absolute age dating on the Earth and Earth materials based on our understanding of radioactive decay. So what this means is that we can use the amount of decay that has occurred as almost like a stopwatch in a rock that allows us to understand how and when that rock formed. So the amount of decay is proportional to the age of the rock. So in order to make this work for calculating the age of the Earth, you need something that is as old as the Earth itself, that has been around since the Earth formed, and most importantly, has remained unchanged since the Earth is formed. So what actually gives us this information is not Earth materials themselves, because they've been subjected to all of the processes that change rocks over time. Erosion, plate tectonics, volcanic activity, the rock cycle, these are always changing rocks and resetting the clocks. So we need something that has remained unchanged. So primitive, and by primitive we mean unchanged, meteorites give us a way, give us an object that has remained unchanged since the beginning of the Earth that allows us to understand the actual true age of the Earth. So these are basically sort of leftovers from the formation of the Earth, and as such, we know these have been around, floating around in space since the formation of the Earth itself, or at least we theorize that. So primitive meteorites give us something to date that has been unaffected by Earth processes like erosion, deposition, volcanic activity, rock cycle processes. So specifically, we use these primitive meteorites and a type of radioactive radiometric dating called uranium lead dating. So uranium lead gives us an age of the Earth of 4.54 billion years. And that's given the proportion of the original radioactive starting material, uranium, to its eventual decay product, lead. And this is based off the half-life of uranium, how long it would take for half of the uranium to decay to lead. This leads us to our current understanding of the age of the Earth, set at about 4.5 billion years. So I talk a little bit about in the lecture about how this number has grown over time. And the only reason this number has changed is because we found older and older material to date. When we were relying on Earth materials, the oldest rock, the oldest mineral, that would be a number that has always basically changed because we kept finding older and older materials that had been unchanged further and further and further back in geologic time. Once we started the shift towards dating meteorites instead of Earth materials, this number has remained constant. So we're confident that we have a really good working understanding of the age of the Earth at 4.5 billion years. Okay, so the next question down here is all about radioactive decay. What are 3 forms of radioactive decay? And what is the effect of that decay on atomic number and atomic mass? So the 3 forms of radioactive decay are called alpha decay, beta decay, and electron capture. These are the 3 primary forms that we're going to be concerned with in our understanding of geologic time. Some individual examples of decay have really short half-lives and are not really applicable to understanding geologic time just because they don't work on a big enough time scale. But these are going to all be examples that, for the most part, do work on a large enough time scale to be beneficial to us in our working understanding of geologic time. So in alpha decay, this results in the loss of an alpha particle, which is the equivalent of a helium nucleus, just 2 protons and 2 neutrons. So if you have a process that's going to just basically sort of spit out this little ball of mass of 2 protons and 2 neutrons, then the effect of this has to be to change the atomic mass. So this is something really important to remember when you're trying to narrow down your options of what kind of decay could it be, given an example. This is the only type of decay that changes the atomic mass. And the atomic mass drops by 4. This also going to reduce the atomic number by 2. So we've defined alpha decay. We've talked about the change in atomic mass and the change in atomic number. So a good example of this might be something like uranium dating. Anything that's going to be really big to start with, like some of those really, really hot, big numbers, high numbers on the periodic table, everything past lead actually is radioactive and definitely subject to alpha decay. And then what happens is every time that decay is occurring, you lose an atomic mass of 4 and atomic number 2. And the reason this happens is because the atomic mass is the sum of neutrons and protons. So to spit out a helium nucleus, that would be a reduction of 4 particles, all contributing to the atomic mass. And then the atomic number by 2. The atomic number is just the number of protons. So you are going to change the name of the element. You would change uranium to thorium, thorium eventually down to lead through a whole series of decay processes because you changed the atomic number. So it's always going to change effectively the name of the element. And then you're also changing the mass as well because you're eliminating both protons and neutrons. You're not replacing anything with anything else. So usually anything dealing with uranium, thorium, etc., is all going to be an example of alpha decay because you're always going to be really substantially lowering the mass of the atom. In beta decay, this results in the loss of a negative charge. You could think of it as the loss of an electron from the nucleus of the atom. So if you're losing negative charge, you're taking an existing proton and changing it to a neutron. And then this is why the atomic mass doesn't change. The reason this remains unchanged is because the total number of protons and neutrons stays the same. If you had something like radiocarbon with 14 protons and neutrons, but one of those protons gets changed to a neutron, then what's going to happen here? I'm sorry. I know I messed this up. Okay. What's happening here is it's becoming more positive. So the neutrons actually change to a proton. My apologies. It's like every time I've taught this so many years, but every time I teach it, I almost have to relearn it myself. So your neutron's changing into a proton. This is because you're losing a negative charge. So your loss of, I had it right the first time. Okay, I'm losing all trust, I'm sure. So the atomic mass is remaining unchanged. The total number of protons and neutrons is staying the same. The only thing that is changing is the atomic number. And so then the atomic number is increasing by 1. Radiocarbon is a good example of this. This is carbon with a mass of 14 that's changing to nitrogen with a mass of 14. The atomic number of carbon is 6. The atomic number of nitrogen is 7. So your atomic number is increasing by 1. So again, this neutron is changing to a proton. I had it right the second time. Sorry, I'm a mess today. I did not get enough sleep last night to be dealing with chemistry. Chemistry is never really my favorite. So we've got 3 forms of radioactive decay. Alpha decay, which is the only one that's going to have a change in the atomic mass. Beta decay, which is going to change the atomic number, but not the atomic mass. And then electron capture, which is basically going to do the opposite of what beta decay does. So I'm very sorry that in the description of this, I definitely, messed this up a couple of times. I managed to, if you mess something up enough, you almost sort of like anti-learn it in your brain, and then you've got to work really, really hard to fix it. So my apologies. I'm confident in this answer, though. It's not getting changed again. So electron capture results in obtaining negative charge, or if you want to think about it as electron. So you're capturing a negative charge. That's why it's called electron capture in the nucleus of the atom. If you're doing this, you're taking something that is positively charged and changing to something that's neutrally charged. So in beta decay, you change a neutron into a proton, keeping the atomic mass the same. You just do the opposite in electron capture. And so this is why in electron capture, your atomic mass is still unchanged. Just realized I got this wrong up here. Atomic mass is unchanged. Atomic number decreases by 1. So potassium argon dating is usually cited as a pretty good example of electron capture. All right. One thing I really like to do when I'm teaching radioactive decay is have a periodic table in front of me, and either having the periodic table, which I don't have in front of me, I didn't prepare accordingly, or having the atomic number for all of these different elements is really critical to be able to answer any questions that I might give you on the exam about this information. So what you'll either have is in the text of the question, I'll give you the atomic number. So I'll say in the example of radiocarbon, where you go from carbon with a mass of 14 to nitrogen with a mass of 14, what type of decay has occurred? You know the mass has remained unchanged, so you know it can't be alpha decay. And then in the text of the question, I would have to either tell you or give you a periodic table so you can find out for yourself what the atomic number for carbon is and what the atomic number for nitrogen is. Effectively, if you're going forward on the periodic table, 6 to 7 or 19 to 20, so on, then it has to be beta decay. Your atomic number is actually increasing. If you're effectively going backwards on the periodic table, then it has to be electron capture. If you're going from 20 to 19 or from 5 to 4, then you know this is your type of decay that has occurred. Okay, so that's the first 3 questions. These are the ones that all relate back to lectures 20 and 21. Like I said, those are sort of the more core subjects to go through. And then with 4 and 5 here, what major changes did the Earth go through in the Precambrian, and then 5 in the Phanerozoic? It really helps to have a geologic time scale to look at, to go over. So what I'm going to do here is I'm going to go back into Moodle, and I'm going to find, yes, I know I'm presenting to everyone. Okay. I'm going to go back into Moodle here. I'm going to find our geologic time scale. Here we go. So under lecture 22, geologic time scale, I'm going to go ahead and bring that up, open it up, and actually cut and paste it, or copy paste it into our review question so we could go through these together. Actually, I'm not going to do that. I'm going to go back and forth because I didn't want to copy the numbers too. So delete that. So going back over to this time scale here, you've got the time scale very, very much skewed towards the Phanerozoic. And then 10 placeholders here with 5 events in the Phanerozoic. That's 6, 7, 8, 9, and 10. And then 5 big events in the Precambrian, 1, 2, 3, 4, 5. So I go through way more than these 10 events in the lecture outlines. You know, I go through a numberable number of events through those lectures. But these 10 events, I'd say, are really sort of at the core. These are probably the most important 10 events. And so these are going to be our answers to questions 4 and 5. So using the time scale under the lecture 22 information. Events 1 through 5 are going to take place in the Precambrian. So that's question 4. And events 6 through 10 take place during the Phanerozoic. That's question 5. So we're going to keep kind of waffling back and forth between the time scale and the text of these two questions here. So what major changes did the Earth go through in the Precambrian eons? So the Precambrian eons are everything that came before the Cambrian time period. The Cambrian time period is the first time period within the Phanerozoic eon. It's the beginning of the Paleozoic and the beginning of the Phanerozoic. And it marks this really, really big shift in geologic time because that's when large organisms started to become preserved in the rock record. Now, we've since the construction of the geologic time scale found basically big, critters that maybe just didn't preserve really well, had more of a very specific way in which they would get preserved that only got preserved under certain conditions. They were found towards the very end of the Precambrian. So this doesn't really mark just the existence of big organisms generally. It marks the existence of big organisms that preserved really well. And our understanding of geology generally, and very much our understanding of the history of life on Earth, is very, very biased towards the events and organisms that actually got preserved in some way, because otherwise we don't know about it. So that's how the geologic timescale came to be and is always inherently a very flawed concept, because it's always going to be biased towards whatever we're able to actually find and see. But like everything else in science, it's the best we can do. So question 4 here, what major changes did the Earth go through in the Precambrian eons? Precambrian being anything that came before the Cambrian period. That's the Hadean, Archean, and Proterozoic. First, you have the formation of the Earth. That, by definition, has to be the first big event. The Earth formed through countless collisions of particles in the early solar system that combined through a process called accretion to form the planets. So Earth formed just like Mercury formed, just like Venus formed, just like Mars formed. And the inner solar system, where you had mainly rock and metal as your building blocks of planets, these little pieces of dust and debris containing that rock and metal collide together and collide again and collide again and collide again until you have these orbiting objects that have cleared their own orbit of all remaining debris. So this process of collisions forming planets continues throughout the entire Hadean eon. That's what we call the first few 100 million years of Earth history, the heavy bombardment period, because it's not like you just shut down this process of forming planets one day and all collisions are then done. We still have collisions on Earth. We still have meteorite impacts. They're just far, far less common, and the Earth is a much more peaceful place because of it, because as time goes on, as we're entering however many million orbits around the sun, the events that the collision events that would have taken place have already taken place. So they become less frequent, but they still do occasionally happen. Okay, so we've formed the Earth. The Earth is still hellish and horrible throughout the entire Hadean period, definitely not conducive to the evolution of life. Although it will be eventually. The Earth has to just cool, and this process of forming the planet itself has to come to a rest. It has to settle down. And that's when we get into the next big event, formation of the Earth's oceans. As the Earth cools towards the end of the Hadean eon, water vapor is able to escape the cooling rock of the Earth's surface. Of rocks that formed the Earth itself also contained the water that would eventually become a really important part of the surface of our planet. So these rocks were something like 8% water. It's a type of meteorite called the carbonaceous chondrite. So the water would eventually degas. That water vapor would escape. It would get into the planet's atmosphere. Then that water vapor would eventually cool in the planet's atmosphere, cool and condense in the planet's atmosphere, and precipitate on the planet's surface, flowing across the surface of the planet, eventually forming rivers flowing into ocean, starting a whole water cycle on our planet. So then this is all further cooling the surface of the Earth, and at a certain point, this would actually cover the entirety of the Earth in a layer of water. So the Earth's oceans are actually older than the Earth's continents, which is kind of like a mind-boggling thing to think of. You know, for anything to really have like the memory and have the longest history with the Earth, of course, it would be the Earth's oceans. So eventually, far, far later on, we're going to get into the continents. I just want to refer back to the time scale real quick. We've covered event 1, which has to be the formation of the Earth, the slow cooling of the Earth leading to event 2, formation of the Earth's oceans. And eventually, we get into event 3 over here, the beginning of the Earth's continents, origin of the Earth's continents, and origin of life. We may never know what and when was the first organism on Earth. We may never be able to say definitively when life on Earth started, but it most likely was inherent with these oceans and with the existence of warm, coastal environments brought about by the existence of the continents on Earth. So the origin of Earth's continents, origin of life. This would have allowed life to really kind of take off. So as the plate tectonic cycle starts, formation of more durable rock, this is felsic, igneous rock, was able to form the first continents, stable, warm coastlines. Allowed life to develop on Earth. So these events are really, really broad. They're really, really spread out through geologic time, but they're all incredibly important for what's to come, both in terms of the geology on Earth and life. So our next event here is going to be event 4, defining the end of the Archean and the beginning of the Proterozoic. And this is something really important to take note of too. These events are always going to be located at the end and the beginning of eons and eras for the most part. Some fall kind of right in the middle of something, but for the most part, you're always going to have a number that defines the end of one eon or era and the beginning of another. And because that's how the geologic time scale was constructed. It's separated based on big events and not arbitrary numbers. So event 4, we call the Great Oxygenation. Oxygen became part of the Earth's atmosphere through the development, almost the invention of photosynthesis in primitive organisms. These primitive organisms were cyanobacteria. They figured out how to undergo photosynthesis. This created oxygen. And in these environments, when you didn't have any major predation, these organisms were able to just completely flourish, really take over the earth and pump over millions of years tons and tons of oxygen into the Earth's atmosphere and into the Earth's oceans. It would have revolutionized the appearance of the Earth. The Earth before this would have been unrecognizable with red carbon dioxide rich skies and green oceans because of all of the iron dissolved out into the water. Oxygen filling up the chemical sink in the oceans would have dissolved out all that iron. It precipitates all over the floor of the ocean in the banded iron formations. And then oxygen in the Earth's atmosphere completely changes the kind of temperature range that you get in the Earth's atmosphere. And it completely changes its appearance. It turns our skies from red to blue. Probably the most important thing that oxygen allows is having oxygen. I'm going to go ahead and capitalize this because it's annoying me. Having oxygen then allows larger life to eventually evolve. Prior to the origin of oxygen in the Earth's atmosphere, you don't really have any way of supporting anything bigger than a bacteria, something that can survive in a no oxygen or low oxygen environment. But having oxygen make up this really substantial part of our atmosphere, 20% of the Earth's atmosphere, means that you have an entirely different metabolic process to fuel the development of life on Earth. So oxygen is very, very important. That's why it's event 5. event 4. Event 5 is called Snowball Earth. Life probably got a decent jump start after the Great Oxygenation event, probably started to flourish, and it's possible that the origin of large-scale life on Earth would have happened something on the order of 500 million years to 1 billion years sooner than it actually did, except something happened on Earth that quite nearly eliminated Earth's life completely. So we think about these mass extinctions as relatively recent things that have happened in just the last hundreds of millions of years. But Snowball Earth was probably the Earth's biggest mass extinction. We just don't really have any information about it. But it definitely would have put this major hiatus on the development of life on Earth. So a supercontinent called Rodinia formed near the Earth's south pole, which caused ocean circulation to stagnate and temperatures to drop on Earth to the point where the entire planet was covered with ice. So there's definitely a theme, especially in the way that I cover and treat Earth history, where supercontinents are always really bad for the development of life. Really bad things happen when all the continents team up and all line up together. This is always going to have really stark consequences for life, because life really has a preference towards these warm environments around coastlines. So not only that, but supercontinent configurations have a really big marked effect on the stability of the mantle, the amount of volcanic activity that's taking place, and in this case had a really stark effect on ocean circulation and global temperatures, causing us to go into the Earth's biggest glaciation event. So I don't know why I decided to capitalize ice down here, but again, I don't know where my brain is today. So later on, we'd get out of the snowball because the position of the supercontinents also triggered all this volcanic activity in the mantle, which then eventually split apart the supercontinent, pumped a bunch of CO2 into the atmosphere, warmed the surface, all happening really, really gradually throughout time, and eventually got us to the kind of stability that allowed the beginning of the Phanerozoic eon to take place and all of the events that would shape life. And so that's going to bring us to the next question on the study guide. We have 5 events here. What major changes did the Earth go through in the Precambrian? And going back to the time scale, again, we can define these as the formation of the Earth, the formation of oceans, the origin of continents and life, the Great Oxygenation event, and then Snowball Earth Rodinia. The next question takes us into the Phanerozoic eon and the next 5 events, 6, 7, 8, 9, 10. And these I cover in lectures 24 and 25. So coming back over here, 5, this is the last question on the review questions. What major changes did the Earth go through in the Phanerozoic eon? These are going to be 6, 7, 8, 9, and 10 on that geologic time scale. So our first event, the thing that really has to define the beginning of the Phanerozoic, being the eon of visible life, phaneros, visible, zoic means life, is this event called the Cambrian Explosion, which is a life diversification event that marks, I just snored, the beginning of the Phanerozoic eon. conditions were so perfect at this time for life that the evolution of life just really kind of like takes off. From our perspective, it looks abrupt, but I mean, this is still processes that take millions of years to take place. But you get almost this evolutionary arms race where life is developing all of these really, really cool things, all of these really cool tactics to become really perfect in its environmental niche so that it can be more successful. So you get lots and lots of different forms of life, and particularly lots of different forms of animal life, which is of course of major importance and interest to us because we're animals. So you have effectively the Cambrian Explosion marking the beginning of the existence of hard shell fossils. We almost think about it as the existence of visible life, even though some of this predated the beginning of the Cambrian period by a little bit. But you can really kind of think about this as almost sort of the beginning of large scale life that's eventually going to look and feel a lot more like our definition of animal life a little bit later. So, beginning of the Cambrian, the reason why they call everything, and from the last question 1 through 5, are all events of the pre-Cambrian, is because this is almost like the beginning of life, if you ignore things like bacterial life. So our next event down here has to be within the Paleozoic period. So within the Phanerozoic, there are 3 eras. We call the Paleozoic, the Mesozoic, and the Cenozoic. Paleo meaning old, Meso middle, Ceno new. Old, middle, new life. So you know anything that's going to define the beginning and end of these eras is going to have to be a big event that shapes life. So throughout the Paleozoic, from event 6 to event 7, we have life continues to evolve and become more complex. Eventually conquering the continent. The specific event that number 7 is pointing out is the origin of plants on the continent, because this is the whole reason we call that period of time the Carboniferous, is because we have plants decaying, producing carbon on the surface, having carbon-rich deposits that get buried with rock and become coal. So during this period, plants covering surface of the earth would eventually become the coal we use today. So, you know, it's hard to cover geologic time and have these individual dates when you know, and events when you know the story's way more complex than this. Life starting as invertebrate organisms being locked in the oceans by the beginning of the Paleozoic, and evolving to the point in the Devonian and in the beginning of the Carboniferous where life would start to evolve to form backbones. Plants would evolve to take over the continents. This gave a source of food for animals that were also covering the continents at the same time, until by the end of the Paleozoic, you have a full modern biosphere on the surface of the earth as well, not just in the oceans. So then by the end, you have life is doing really, really good, but this also coincides with the timing of another supercontinent. So this next event here is what we call the Earth's largest mass extinction. It's the end Permian mass extinction. Once upon a time, my paleontology teacher called this her favorite mass extinction because everything dies. So that's really exciting to a paleontologist. They kind of rely on everything dying all at once and leaving lots and lots of fossils in one easy to find location, because that enables them to understand more about the development and the history of life. So the Permian mass extinction would be right here. This is what we're calling event 8. This defines the end of the Paleozoic and the beginning of the Mesozoic. And this is when 95% of marine species, actually 95% of species generally on Earth, went extinct due to these different warming events brought about by massive amounts of volcanic activity. This massive volcanic activity in a place we now call today the Siberian Traps volcanic activity. We call this the Siberian Traps, where this volcanic activity was taking place. This volcanic activity was probably triggered by the construction of supercontinent Pangaea. Again, to sort of paint this broad picture here, you have all this great stuff going on with the evolution of life, both in the oceans and on the continents. And then the continents inch closer and closer together, eventually colliding to form one big supercontinent Pangaea. Anytime you have a supercontinent configuration, this is going to spell trouble in the ocean. You probably had some ocean stagnation happening at the same time. But the big thing that happened that probably triggered most of the mass extinctions that took place during this time was that these continents being all piled up on one part of the Earth created a lot of buildup of heat in the mantle underlying the supercontinent, which then led to all this volcanic activity, producing a lot of CO2 in the Earth's atmosphere, which then caused atmospheric warming and warming in the oceans. And particularly the species in the oceans at this time that couldn't get up and really move around, that were incredibly vulnerable to changes in sea level and changes in temperature in the ocean, weren't able to adapt to survive, at least not quick enough, and they went extinct as a result. So that is the Earth's first big well, actually not first big mass extinction, but let's call it the largest mass extinction, because compared to the other big extinction events, the ones that we talk about, the ones that we don't talk about so much, this is the one that caused the most catastrophic damage to Earth and life on Earth. So the life that remained after this mass extinction that was able to survive eventually thrived, evolved all on its own to form many different species in the oceans and on the continents, but eventually led to the development of dinosaurs. So the next big extinction event that we have to talk about is their extinction. So this entire time period between events 8 and 9 is really what we think of as the era of the dinosaurs, slowly evolving, getting bigger and bigger after the end of the Permian and the beginning of the Triassic. So you don't immediately see these dinosaurs in the fossil record. They would really come about more towards the very end of the Triassic, coming into their own in the Jurassic, and really taking hold of the Earth during the Cretaceous. They were able to rule the Earth for millions of years before eventually circumstances would lead to their doom and the doom of something like 70% of species on Earth at event 9 here, which marks the end of the Mesozoic and the beginning of the Cenozoic. So this end of the Mesozoic is second largest mass extinction. Some refer to it as the end Cretaceous mass extinction. Or let's just simply call it the dinosaur extinction. Dinosaurs and 70% of other species on Earth went extinct, most likely due to a massive asteroid impact. So this massive asteroid impact hit the southern part of the modern-day Gulf of Mexico, near the Yucatan Peninsula. It was very difficult to see for a very long period of time because it's almost entirely submerged underwater and in an area of the world where you have a lot of erosion taking place, so it didn't get preserved really well. It was first theorized by Walter and Louis Alvarez as being a likely cause for the iridium anomaly that they were seeing preserved within rocks. They said something that could potentially cause that would have been a really, really big asteroid impact. Later on, after this was proposed by them, they eventually found the impact site. It's called the Chicxulub impact site. So all of this would have caused a drop in temperatures, so much so that the dinosaurs really couldn't evolve fast enough to keep up with that drop in temperatures. And so I won't say that all dinosaurs went extinct during this time. I think about it more like most dinosaurs went extinct during this time, because you can really think of all modern birds as being the evolutionary descendants of dinosaurs. So then the life that takes over are the survivors of that mass extinction. I'm sorry, of this mass extinction of number 9 here. And so the life that would evolve to conquer the earth after this would evolve into flowering plants, grasses, mammals, and birds. These would be the modern organisms that I think of when I think about the Cenozoic. I think Google Meet's probably trying to shut me down again. I'm going to shut that down. Yeah. So going back to the time scale again, coming up towards the end of this, we have a lot of stories to tell within the Cenozoic, but in our very, very brief version of geologic time, we kind of tend to gloss over that, just saying that birds, flowering plants, mammals really did well and flourished and survived and evolved during the Cenozoic. Hit a little bit of a stumbling block with the most recent ice ages, but lived to present, even past probably one of the most difficult points in the evolution of life on Earth, and that is the development of human civilizations. So this last event, number 10, really refers to 10,000 years ago. the last ice age ends and human civilizations begin. When you compare just 10,000 years ago to the entirety of 4.5 billion years of history on planet Earth, 10,000 years is nothing. It's something on the order of 0.00001% of all of geologic time. Humans have been around building things, creating civilizations. So we exist on Earth today to be able to look at this extensive past on Earth and hopefully be humbled by it. So this is the way I like to kind of cover it. We, in a good way of going through and reviewing this, is to take the many events that I cover across those 4 lectures and really just sort of condense it down to these are big events, because it does a couple of things. It shows you what are the big events that mark the beginning and end of eons and eras. And it tells you at least a very brief story of the history of the Earth itself. So I'll go back here real quick. That's questions 1 through 5 of the review questions. Hopefully when you went about doing this and putting these things in your own words, you got something similar. If not, take the time, adapt that. And I think you guys are going to do really well on the Unit 4 exam. So very good luck to you all on the final, and please keep in touch if you have any questions for me. Everybody have a great day. Bye.